Hello everyone and welcome back to my channel. I'm Gagana B from Sri Venkateshwara College of Engineering, Department of Data Science. Today I'm here to explain a concept from operating system, so-called Amdahl's law. Okay, today we'll be learning about the introduction, the law in nutshell, the formula, understanding the formula, implications of the law, real world examples, and then we would be concluding it with a small conclusion. Heading towards introduction. In the first page world of computing, the quest for ever increasing speed is recklessness. We throw more cores, faster processor, and bigger memory at our problems, hoping for lightning fast results. But there's a fundamental principle that governs the performance of implement. That is so called Amdahl's law. The law in nutshell. Amdahl's law, formulated by Jean Amdahl in 1967, states that the overall speedup of a system when improving one part is limited by the fraction of the time that the improved part is actually used. In simpler terms, no matter how much you optimize a portion of a system, the overall performance gains are capped by the time spent on the task that cannot be parallelized. The formula. Here's the formula. I divided by f plus I minus f divided by n. Speed of the improvement in execution time. F is the fraction of the task that can be parallelized. N is the number of processor or resources used. Understanding the formula. Moreover, first when we understand it, we can then apply it in our real world example and then create more solutions for the unknown problems. Heading towards, this represents the parallelizable portion of the task. Think of it as the instruction that can be divided and run simultaneously on multiple processes. I minus f, this is the sequential portion. Okay, so what is this? F is the representation that represents the parallelizable portion of the task. Okay, think of it as the instruction that can be divided and run simultaneously on multiple processors, whereas this I minus F, I repeat, I minus F, this is sequential portion, the bottleneck that cannot be parallelized. It could be a file, input output, communication overhead, or any task that must be run in a specific order. And number of processors or resources you can throw at any problem. Implications of the law. Okay, what are the implications of the law? Let's see. Diminishing results. Adding more processor will initially provide significant speed up, but the gains will become smaller as you approach the limit imposed by the sequential portion. Throwing endless processor at a problem won't magically make it super fast. Identifying the bottlenecks. Amdahl law emphasizes the importance of identifying and addressing bottlenecks. Optimizing the parallelizable portion is crucial, but neglecting the sequential part can significantly limit overall performance gains. Here, these are the two implications. It is diminishing results and identifying bottlenecks. Heading towards the real world examples. No matter what way we learn, there's a need for us to imply it in our real world, in our day to day life, whenever we come across different sorts of scientific problems. Only then we can apply our knowledge and be benefited from what we have actually learned. Some of the real world examples are image processing and scientific simulation stimulation. Image processing, while applying filters to millions of pixels, can be parallelized across multiple cores. Loading the image and saving the results are sequential tasks. Amdahl's law dictates the maximum speed up achievable. Heading towards scientific stimulation, complex stimulation often have significant parallelizable sections, but communication between the processor and data input-output can become bottlenecks limiting the overall speed. Heading towards the conclusion of this very beautiful topic, Amdahl's law is a fundamental principle in understanding the limit of performance improvements in parallel system. By acknowledging its implication, we can approach the optimization strategy strategically, focusing on both parallelization and bottleneck reduction for truly impactful performance boost. Thank you for watching my video. Please do like, share, and subscribe because your likes, your views matters a lot for me because it adds on to my academic marks. Thank you all for giving your precious time for listening to my presentation. Thank you once again.